We want to find the fourth degree Maclaurin polynomial, and we're going to use it to approximate natural log of 1.1. So if we want a fourth degree, that means we need to get to the fourth derivative. So I'm going to go ahead and just rewrite the original function here, and let's come up with our first four derivatives. So this would be 1 over x plus 1. Now, when you're taking the derivatives, I would think of it like x plus 1 to the negative 1. So my second derivative is bring down the 1, reduce the power by 1. And I'm going to just then simplify it because I know I will need to plug in numbers. My third derivative is bring down the negative 2, reduce the power by 1. So this is this. And then my fourth derivative is bring down the negative 3, reduce the power by 1. So that's going to give me this. And remember, what we want to do is I want it to be centered at 0, so I'm going to go ahead and plug in x equals 0 to find all the values of the derivatives. If I do that, the value of natural log of 1 is 0. This one will give me 1. This one will give me negative 1. This is 2. And then this is negative 6. So my fourth degree polynomial is first term is 0, which I'm not going to write. And then we have the first derivative minus the second derivative squared times x squared over 2 factorial, 2x cubed over 3 factorial, minus 6x to the fourth over 4 factorial. So this is my fourth degree polynomial. And then if I want to approximate natural log of 1.1, be careful here. Notice the function that we're working with is natural log of x plus 1. So this polynomial is an approximation for natural log of x plus 1. So to get to natural log of 1.1, really you are going to plug in 0.1 for x. Right? 0.1 for x will give me an approximation to natural log of 1.1. So if you punch that into your calculator, you should get approximately 0.09530. So notice natural log of 1 point is approximately the value of this polynomial at 0.1. Okay, now let's go ahead and write a third degree for a function. And here I'm actually giving you all the values of derivatives. The third degree polynomial would be f of 0, which is 5, first derivative times x, second derivative x squared over 2 factorial, third derivative x cubed over 3 factorial. Now, then it says to use that polynomial to approximate this antiderivative. So I'm going to integrate the function from 0 to x, and notice here it says to use f of t. So instead of using x's, I want to use t's for my equation. Over 2 factorial plus 4t cubed over 3 factorial, and all in terms of dt. And I'm going to go ahead and integrate this. So this is 5t minus 3t squared over 2 plus t cubed over this plus 4t to the fourth over 4 times 3 factorial, and we're going to go ahead and plug in the bounds, and you can go ahead and simplify a couple things here. So I end up with 5x minus 3x squared over 2 plus x cubed over 2 factorial times 3 plus x to the fourth over 3 factorial, and then everything else becomes 0. So this would be the antiderivative of this. Okay. Now we're going to go ahead and find the Maclaurin polynomial for a couple different functions. So remember, whatever degree that I'm asking you to find it for, you need to come up with that derivative. So here, I always rewrite the function here at the top so I don't forget about that first term. I need to come up with the first four derivatives. So this is negative e to the negative x. Second derivative would be e to the negative x. Third derivative, notice it just alternates here. And I want the Maclaurin, which means we're centered at 0, so I'm going to plug in 0 for x. So if I do that, this is 1, negative 1, 1, negative 1, 1. And my fourth degree would be, I'm going to write it over here. First term is 1, first derivative times x plus second derivative x squared over 2 factorial, third derivative x cubed over 3 factorial, etc. So this is your fourth degree polynomial. Okay, let's try the next one. Same thing, I need to come up with the derivatives, but I'm only looking for a third degree, so I'm going to go ahead and come up with the first 3 derivatives. I'm going to write the original function on the top to start. The derivative of the sine of pi x is cosine of pi x. Don't forget chain rule, you need to multiply by pi. Second derivative is negative sine of pi x, but you need to multiply by pi again, so you end up with a pi squared. Third derivative is cosine of pi x. Sine will stay the same, but you multiply by another pi. And again, Maclaurin, so I'm going to plug in 0 for x. So this is 0, pi, 0, negative pi cubed. My third degree is going to be, starting with the 0, I'm not going to write that, so first derivative times x to the first. Second derivative is 0. And then pi cubed, x cubed over 3 factorial. Okay, this last one, C, you can do the same way. You can go ahead and create the first 5 derivatives, but there's something special about this one. Notice this function is written in the form of a over 1 minus r. So this is really a geometric series. It's the sum of a geometric series. So if you recognize that right away, you can identify that your a is 1, r in this problem is x. So really, I know that my first term is 1, and really all you're doing is multiplying by x every single time. So this is your series. It just happens to be a geometric, so if they give you that sum, I can identify it really easily. So I can do that without taking the derivative.